Should I announce? Right. We are very pleased to have Cheuk Tsang of Université du Québec, Montréal, speaking about minimum entropies of braids.
Thank you for the introduction. So today I want to talk about some joint work with a student, Xiangzhuo Zeng, who also goes by Andrew. And this is work about braids. So I suppose I should start by telling you what braid is. Braid for today is going to be a bunch of strings inside a cylinder. So let's say you have 4 strings and they sort of went around the cylinder in some kind of monotonic way. For example, like this. So this would be a braid with 4 strands in general. With n strands would be if you have n strands going from the bottom to the top. And the way I like to think about braids is you can start with the bottom face of the cylinder and then sweep upwards. And then what's going to happen is that you're starting with this disc with 4 points. And as you sweep upwards, these points are going to move around. And so that's going to determine a map from the bottom face to the top face. And the dynamics of that map, how these points move around, is exactly dictated by how the braid looks like. So a braid determines a morphism of a n-hole disc. So specifically, I want to think of these, I want to remember the data of these points as holes. And as I sweep from bottom to top, I see the holes move around as opposed to points. That just makes it easier to keep track of.
We have to homotopies.
That's right. So it's a very good observation. This is only well defined up to isotopy. So let's look at some examples. So here's a braid with 3 strands. It's the most boring one. It's a trivial braid where you just have no crossing. So when you sweep the bottom face to the top, you just get the identity map. Here's a second example. This is slightly more interesting. You have 2 strands that wrap around each other. So this would induce a twist around the curve. So if you draw out the disc, it's going to have 2 holes corresponding to 2 strands. And let's see, I'm sweeping from bottom to top. And so they're winding around in the clockwise direction. Okay, so third and final example is what is known as the French braid. This is
Sorry, in this picture, what happens to the in the mid between the two circles?
at this point.
Yeah.
So let's say it stays constant.
Yeah, and around it is somehow it's a circle location around it, or?
Yeah, so let's say for concreteness that the map only moves points inside this sort of annulus region. So it takes this hole to this hole, sort of this hole, maybe with a few more iterates as you do more twists. So the important point is that everything is what the homeomorphisms are just defined to isotopy. So there is some built-in ambiguity as to what the map is. But such is life in topology, everything is only well defined to isotopy.
does homeomorphism understand that you twisted it 3 times versus?
Yes, right, yes, it does. You just, you iterate this as many times as you twist.
It's a family of homeomorphisms, so I don't quite understand.
It's just-
Is it from top to bottom? Because then
It doesn't matter. Let's say we go from bottom to top.
is it the homeomorphism between the bottom configuration to the top
Mhm.
configuration?
That's right.
But then it wouldn't distinguish how many times you twist. This information is lost.
Why wouldn't it? So if it just had one crossing, then it would be one twist, I guess 1/2 twist. And if you have 2 crossings, then you would twist and then do it again.
It's,
What do you mean?
it's not a good, like, I mean, it's gonna, the homeomorphism will know how many twists you did. You can try to like look at, I don't know. Say something that like an interval that goes between them and like try to look what is its image gonna be, and it's gonna look differently for a different number of twists.
Well,
So
here's something
there's
that's,
a sort of time variable in the homeomorphism. No.
No, so like the way you should think about homeomorphism, like you don't really think about what happens in between, like you just. Like you have things at the bottom and like you look where they end at the top, that's gonna be the homeomorphism.
Okay.
And like what happens in between is gonna kind of dictate what that homeomorphism is. But there's no time, there's just going from top to bottom to top.
Maybe think of it
So
as,
again, so how is the number of twists
But I
affect
think
this?
you can think, if you ignore this region between two circles, you can think.
yeah, so here's something that might help.
All to kind of show what happens.
So
Well, this is 3 homeomorphisms.
Exactly.
that's right. So, and the final homeomorphism is a composition of these
Okay.
3.
So the final does not know how many.
Yeah.
It does, because it's a different homeomorphism than if we just do it once.
If you just draw an interval, I think it will be clear.
Yeah, like, do you know what you mean by interval?
No. What do you want me to draw?
Well, I was just like, kind of the way you could imagine what it looks like is like. If you look at this interval, if you do it once,
Oh.
and now I don't know which direction, but you know what I mean?
Okay, so if you twist once, this is gonna be difficult for me as well. Let's see how this goes.
I kind of imagine what happens,
Oh, okay, so there is a region, because there is a region where it's
yeah,
conserved, then you can.
and now if you do it twice, then it's gonna be.
Okay.
So outside of an open set, presumably I can take this, I mean, okay, it's defined after isotropy, but presumably I can take it to be smooth.
Yeah, you can
And
make it.
3 times just the triple speed, so.
Sure. You know what? I can do this.
Sure.
But yeah, as you do more of these, then this blue interval is gonna get more and more wrapped around. Right, okay, so I had the French braid. That. And the induced homeomorphism, there's going to be a composition of 2.5 twists. So you first do a half twist around these 2 punctures, and then you do a half twist around these 2 punctures. Because that corresponds exactly to the 2 crossings. So as you sweep from bottom to top, you first interchange these 2 holes, and then you interchange here too. And right, so this is called French braid. I think this is one way of braiding a hair. Even though, as you can see, I have no experience in my hair, so I will.
I cannot with your past experience.
And then this also has a name, it's the taffy pulling. If you look at a machine that pulls taffy, it has like three things, and then it spins one and then the other, and then repeats that over and over again. Okay, so that is the protagonist of the story. What we want to study is the dynamics. What we want to study is the dynamics of braids. So want to study braids. And more precisely, we study the dynamics of braids via the induced homeomorphisms. And for the purposes of today, we want to study the amount of dynamics that's contained in a braid. So, amount of dynamics today. So one observation, and this is intended to be not very precise, is that the more complicated your braid is, so logical complexity, of the braid usually leads to dynamic complexity of the braid. So for example, if you had a braid, you could repeat the braid multiple times, like what I did here, just do the same twist over and over again, then you would get more and more dynamics in your braid. So in one direction of the spectrum, you could get a lot of dynamics by just doing your braid over and over again. Just do more complicated braids. The more interesting end of the spectrum is the lower end. So we want to know what is the least amount of dynamics that's contained in a braid. And that would be the subject of today's talk. Except not really, because if you think about it, this question is trivial. Because you have the trivial braid. And so the least amount is just going to be 0. And so let's just make it more interesting, say a non-trivial braid. And also, I have to make this precise because, well, what do I mean by least amount of dynamics? So we're going to quantify everything by this notion of topological entropy. And this is the part where I worry that I'm the person in the room least qualified to tell you what entropy is, but I'm going to try. So consider a homeomorphism on a compact surface. And let U be an open cover. So consider the following open cover, which is obtained by taking U, inverse U, and then pulling back the open cover. Doing it again, doing it n times, and then taking the common refinement. So and I'm going to let denote this by these. Oh, maybe I should say what refinement actually means. So precisely, refinement means that this UN.
It's arbitrary or it's finite.
Oh, right. Sorry. Finite.
Okay.
Right. So this UN is going to be another finite open cover, and its elements are going to be of this form.
Those are different views, right? Okay,
Yeah, so
but
each UI. This. So this thing comes from this open cover, which is significant intersect. So I'll consider the least number of such open sets. That suffices to cover S. And the entropy, get the order of my limits correctly. It's topological entropy. On the right, that's small h f. Take the supremum over open covers, then the limit for n of okay, so this is the topological entropy. So I'm not really a dynamicist, and this is just abstract limits to me. How I usually like thinking about this is, well, I look at the elements of this open cover, and what I do is I think of these things as itineraries. Meaning, if you take a point in this open set, it means that this point started in U0, and when you apply F, it lies in U1. And when you apply F again, it goes to U2 and so on. So this is really a sequence of elements in U that records the trajectories of the points. And so this number here, you should really think of as the number of itineraries of points in S under F. So the larger the number of itineraries, the more options a point could have in terms of its dynamics under F. And the topological entropy is measuring the exponential growth rate of the itineraries. Well, okay, here I guess I'll just say length n itineraries. And right, so the more complicated the dynamics of your map is, the more options, the more itineraries you're going to get. The larger this exponential growth rate, the larger the topological entropy. So this is a good way of measuring the dynamic complexity of a homeomorphism. Well, of course, our homeomorphisms are only well defined up to isotopy. So let me define the topological entropy of a braid to be the infimum of all representative homeomorphisms. So that's what I mean by least amount of dynamics. I want to minimize of a non-trivial braid. Okay, so let's just, well, are there any questions at this point?
Can you give an example?
Yeah, I'm just about to do that. Okay, so we are going to look at these examples. Okay, so first example, the identity map. If you run this definition on the identity map, you will see that UN is just U for every N. Because, well, when you pick the intersection, either you get back an element of U or you just get the empty set. And so what happens is that, oh, sorry, rather,
Get intersection.
yeah, you get intersection. So it's going to be bounded from above in that case. If U has n many elements, and this thing is gonna have at most 2 to the n many elements. So this thing is gonna be finite. And when you take the exponential growth rate of something that's bounded from above, you get 0. And so the topological entropy here is 0, as you might expect. has trivial braid, has trivial dynamics, has trivial entropy. Okay, now what about the twist map? I claim that the entropy is also going to be 0 in this case. One way of convincing yourself that that's true is seeing that I could take this representative homeomorphism to be supported inside this annulus. But there's some twist inside this region. And if you are a open set, well, if you're an open set that lies outside of the region, then your basically identity and the exponential growth rate is going to be 0 by the same kind of argument. Now, if you are an open set that intersects, maybe I should use a different color, that intersects this region where the dynamics is actually happening, then as you apply the twist, your open set is going to get twisted around. This. Where's the purple? And when you intersect,
You perform two twists.
yes, 2 twists. And when you compare it with the original open set, you see that the number of different intersections you could get is going to grow at most quadratically in the number of twists that you do. And so what ends up happening is that here,
Wait, why most quadratically?
right, because if you did another 2 twists, so this has of 2 intersections, and if you do another twist,
There might be a better color than blue.
you know what, let's just symbolically draw this as an interval because it's gonna be easier for everyone. And while I'm there, I'm going to switch the colors a bit. So the original thing is blue. If I do one more twist, well, if I did 1 or 2 twists, I guess I would get this. If I did 4 twists, get this. So if you compare, so this is F squared. The green is just 1. Let's say.
It feels linear, why is it quadratic?
Right, sorry, the intersections are linear, but now
Oh,
you also have to sort of
yeah.
intersect among all the iterates. And so you're sort of summing a linear thing over a linear number of terms, so it's quadratic. So let me write this down. So sort of like linear. If you all these intersections, this would still be quadratic. I think it should be n squared for 2, but whatever, who cares? The point is that the exponential growth rate is 0.
That's one, so for one open set, I can see this picture, right?
Sure, but because my open cover is just a finitely many elements, you are going to be able to run this argument for any pair of open sets that exists in here.
Sorry, can I ask a trivial question about the trivial case? So, if my U is 2 overlapping open sets, there are some points in the itinerary I can write arbitrarily one, two, or any combination of
Right,
any
so,
sequence, so that would be 2 to the power n, and then I'm getting log 2 as my entropy.
So
Yeah.
it's not the same end though.
so that's why you have to say least number of open sets here. Like this is just morally what this number is. It's not exactly what it is.
Okay.
You're sort of also accounting for the fact that if your map is identity, well, it's identity everywhere, then the dynamics of this point should not be different from dynamics of this point because they're just neighbors in an open set where the map is sort of doing the same thing.
Getting some sort of equivalence classes of itineraries.
In a way, yeah. Right, so return to someone asked what happens to other well, if you look at other elements of your open cover. So what's gonna end up being true is you could run the same argument and show that the number of sets of this form is going to be bounded polynomially. So if not quadratically, then maybe cubically. No, it's gonna be quadratic, but then with a constant term where the constant depends on the number of elements of U. But here, because you're taking the limit before taking the supremum, you're when you do the limit, it's 0. And when you take the supremum, it's still 0. Somehow this works itself out. I mean, again, I'm not really dynamicist, so this is almost a little bit magical to me. But it works out. It's a good measure of dynamic complexity. And in this case, when you apply it, you get 0. Okay, so, well, that answers our questions, doesn't it? So the answer is also 0. But you know, we want an interesting question. So let's do this. What is the minimum non-zero entropy of a braid?
What do you get for the French braid?
Yeah, so I'm gonna get to that right now. That's a terrible noise.
But is this argument, so this is gonna be for any day twist?
For any Dane twist around curve, yeah, so in fact, you could even get something like if you have 4 strands and do this, then you are twisting along 2 disjoint curves. You can run the same argument.
So any like twist along?
Yeah.
Or any abelian group?
Well, your abelian group could be cyclic.
Classes.
Like, say again?
Abelian group of mapping classes.
Well, your abelian group could be just cyclic,
Yeah.
consistent. I'm gonna show that this has non-zero entropy, but if you take your
Any element generates a.
Yeah.
abelian group.
generates it, yeah.
Any element generates an abelian group.
Okay. Not so.
Okay, right, so how do you compute the entropy here? So there's this really cool observation that you could pick a torus and then skewer it. It's not a good picture, skewering torus. Erase the wrong torus. Okay, so a torus, you skewer it, and then you did a 180-degree rotation. And then what you're gonna get is just a little bean thing, like this. But when you take the quotient under this rotation map. And this bean thing, when you draw out the places where you skewer it, is exactly this disk with 3 holes. Well, it's a sphere with 4 holes, and if you open up one of the holes, it's this 3 holes. And you can draw this red and blue curve on it. And it's gonna look something like this.
Wait, but there is a difference between outer. hall and inner halls.
There's a very subtle difference.
Like,
We're gonna pretend.
for one of them, you have to fix the boundary and for the other
Yeah.
ones, you don't.
But so how do you do to get from the left to the right? I mean,
Yes, so here I'm taking a torus, skewering it, and then
skewing?
taking an axis that intersects it in 4 points.
Okay.
Just take a bagel and put it on.
Yeah,
Yeah.
just flip it around and then take the quotient under this map. So this turning it around action is free except on these 4 points.
Okay.
So if you draw out the 4 points, you take the covering space quotient, you get this. And so going the other way, when you lift the red and blue curves, you're gonna get an arrangement like this.
That's like, it would be relative to this.
We should have, yeah, roasted some bagels.
And also like that thing over
My
there, we didn't do
sausage
that with the
looked like
sausages like that. Could have been the way to do it.
So if you did a half twist along the red thing, when you lift it, you're gonna do half a twist on this red, half a twist on this red, and so they will combine to give you a full twist on a curve of this homology class. And now you can identify the torus with the unit square with opposite sides identified. And then let's say this red curve is this particular curve, homology class. And then the blue one is this one. So like I reasoned, the lift of the red half twist would give you a twist around this red curve.
You have two red curves.
But they're in the same class, I guess.
Yeah, they're in the same class. These things are, so the half and the half combine to give a full twist. And then the blue twist, the blue half twist lifts to 2 half blue twists, which combines to give 1 full twist along the other direction, which has the matrix representative form. And because you're taking a composition, you multiply the 2 matrices, you get this matrix acting on the torus.
So there is generally, maybe that's a question about topological entropy. Like if we have some dynamics in a
Yeah.
cover and then like there is a.
Yeah, I was gonna mention it. So the idea here is that you want to take the lift of this map under the covering and then use the fact that the entropy is preserved under such an operation. But that still leaves the question of computing the entropy here. And what turns out to be true is that you could pick a representing homeomorphism that realizes the entropy very easily. And the way you do it is, well, this thing here, 2x2 matrix, has 2 eigenspaces. There's a expanding one, and then there's a contracting one. So it turns out that the eigenvalues here are the golden ratio squared. And its inverse. And if you look at the eigenspace of the eigenvalue that's bigger than 1, and you folate the square by parallel lines, then this is of the expanding direction, and in the other direction it's contracting. And what's gonna happen is, well, one thing that's true is that you can actually compute the periodic points of this map. So the period n points of 1, these are going to correspond to solutions of this thing. Because when you compute the period n point, what you're doing on the square torus is that you are
What is the relation between periodic points and entropy?
if you have a periodic point, then that gives you an itinerary because you just follow that periodic point around. And so that at least gives you a lower bound.
A lower bound.
Yeah. And it turns out in this case, you get equality, but let's say I'm just interested in showing that this has non-zero entropy.
I see.
But so I was explaining how you figure out the period endpoints, and the way you do it is on the square torus, you would solve the equation like this. So suppose this VW is the period endpoint, and you did your map 2, 1, 1, 1 n times. You want to get back to the same point, but you're on the torus, so everything is mod C2. And so you solve this equation by just computing these points, and I guess you also have to mod C2 the upshot is that the number of period endpoints is going to be equal to trace 22, and this grows exponentially. Phase u to m, where mu is growth ratio.
So you have log mu squared is your.
That's right. So the entropy here okay. Sorry, I went a little quick, but I realized I'm going slower than I thought I would. Let me show you one more example, because I think that's going to be important. Okay, so I have here a braid with 12 strands. And my braid is, well, I'm not going to tell you what the braid is, but I'm going to tell you what the underlying homeomorphism is. It is a composition where you first do a half twist on the red curve, another half twist on the blue curve. So just like the taffy boolean map, but just on these 3 punctures. And then you do 1/4 of a rotation on this disk. So you rotate by 3 clicks. And so this is what's called the Ferris wheel over, well, in this case, and to be more precise, this is of a 4-fold Ferris wheel. And if you go through the definition of the topological entropy, it turns out that what's going to happen is that by doing your taffy pooling map in 1/4 of the surface and then rotating it elsewhere where you don't do anything along the remaining 9 holes, you are sort of diluting the entropy by 4 times. And so you can compute that the topological entropy here is 1/4 of that entropy. And in general, you could do this with an n-fold Ferris wheel. And you would have 1n amount of entropy.
So you want to strip the number of braids for the question to make sense, or?
That's right. So going to yet again modify the question of an n strand. Okay, so we finally gotten to the question that we want to answer. Let's talk, and to convince you that we have finally got to a meaningful question, let me tell you some results that are known about the question. So here's a collection of known results.
What was the motivation for this question?
Sorry?
What was the motivation?
The motivation is to study the dynamics of braids. In a quantified sense. Yeah. There are some underlying motivations from Teichmuller theory, that kind of thing. But I will get to that briefly near the end of the talk. So.
Show up in these like these flows where you have the, you know, the axes that you can. I don't know. Anyway, I could see how they might show up in some flow stuff.
Oh yeah, they show up in close up. I'm gonna give this a name so that I could write the theorem easier. I'll call this. Theta.
We teach it like flow stuff, so.
What?
What is this letter? What is this?
Eta. I'm just giving this a name, the minimum.
Okay,
maximum.
Chichuk likes flows and they show up.
Okay, so
Unsurprisingly, kind of thing.
for a free strand braid, turns out the taffy pooling map gives you the minimum entropy. The soft classical for 4-strand braids. Turns out this is the log of the largest real root of the following polynomial. So this means largest real root of this polynomial.
So is this also something that comes from lifting something? Yeah, this hyperelliptic
No, it's
position? No.
sorry, your question was that
Whether in like 4 strands, you also take a lift, but I guess you would.
you could always take a lift, but it would not lift to a torus
Yeah, it
if
would
it's
lift,
4 strands.
yeah.
What is the minimum polynomial of the square of the golden ratio?
Oh,
I mean, if you press it the same way.
this is what you're asking? No, sorry, no, 2. This is what you're asking?
Yeah.
Okay, oh, right, sorry, this is due to, so in 2002, and in 8 and 5, that's I and so on. 2006. And then 86, we have this one. 87, 88 also known.
Please concrete examples for all of them. At all of those cases, there are concrete examples like.
Yeah. Yeah, so this minimum.
Some polynomial of a matrix or something like this.
Yeah. Don't know. 2011. Okay. So what me and Andrew did was that
How much how complicated do those minimal braids get? Like, are they still like kind of sort of simple like this one, or do they get a little more complicated?
They all have a particular form. I can actually draw you that form. So. So this box, what's happening in this box is that you have n strands and you basically do one n of a twist. So it's off there where you do one half twist, here you have n strands, you do one n of a twist m times.
Where M is what?
Where n, well, n depends on n. This two, if n is odd, 2k plus 1, if n is divisible by 4 equals 4k, that's this is a family of examples found by Ranaka Ken and Vance. So for all except this one, they are attained by their examples. So this one is a twofold Ferris wheel of this one. Sorry, what's that? Yeah, so here you can actually rewrite this.
So it should be the same.
Oh, then eta 2, what's the difference between eta 3 and eta 4 now?
They have 3 and eta 4, so the powers here are 3, 2, 1, 0. It's 4, 3, 1, 0. But yeah, as you can see, there's some high degree of pattern here. But and so eta 6 is the twofold Ferris wheel of this thing. Okay, so what me and Andrew did was that we found eta n for basically all the remaining values of n. Eta n equals this n equals 1. Well, we did for almost all remaining n. We left out 3 remaining values. And this is sort of just an artifact of how we did this. We suspect that the same expressions are true for the remaining 3 values as well. Right, and so these two are attained by these examples, and then this one is a twofold Ferris wheel cover of this one. And so in other words, we basically solved the question basically completely, aside from these 3 values, but we expect that in the future, someone can just come along and extend our methods a little bit and it would suffice to solve the remaining three cases as well.
Akakin and landscapes, not two Ferris wheels, they,
No, they're not.
if they're two different.
Oh, sorry, this is also two cases. So was that your question? You could show that this is not a Ferris wheel of any grade.
Okay.
Okay, so I will now say a few words about how we prove this theorem. Okay, so here is a theorem by Nielsen-Thurston. And it gives a classification of surface homeomorphisms on a surface. Oh, sorry, surface homomorphisms on a compact surface. Say, so every homomorphism on a compact surface is isotopic to one of the following of one of the following three types. So your homomorphism to isotopy is either finite order. So finite order means you raise it to some power, you get the identity. Second option is that it's reducible. This means that there is some essential multi-curve C that is preserved. In fact, you can make it fixed by homomorphism. So the picture here is if you had a surface, if you're reducible, you're going to get some curve like this. That is fixed by the homeomorphism. And so what you can do is you could reduce the homeomorphism to the two pieces. So hence the name. And the third case is pseudo-Anosov. So here pseudo-Anosov means that there exists a pair of measured singular foliations and that's U, so that F contracts LS by some number lambda with 1 and expands the other foliation by the same number. So I don't really have time to unwind completely that definition, but instead let me tell you that that taffy pulling map is an example of a pseudo-Anosov map. And up here, the green foliation is secretly LS. The S stands for stable. And by definition, this is all the directions that are contracted by this map 2111. And the purple is by definition all the directions are expanded by the map. And in this case, this lambda is the spectral radius of my matrix, which is mu squared. And so more generally, if you're given a braid, you're given a homeomorphism up to isotopy, you can actually assume that, well, if it's pseudo-Anosov, then it's pseudo-Anosov. If it's reducible, you could reduce it to all of its pieces each piece, you could then run the trichotomy again, reduce it to its most basic blocks, and then each of those would define an order of pseudo-Anosov. And the topological entropy of the braid, this is going to be the log of the minimum value of this lambda over all the pseudo-Anosov pieces. So that's consistent with this computation up here. Well, we call it computation, small facts that I told you to believe me in. Okay, but the upshot of this theorem is that if you want to minimize the topological entropy, it really suffices to think about pseudo-Anosov braids. And one thing that's true about pseudo-Anosov braids is that there's this technology of train tracks. And that's what the picture I've been drawing is supposed to show you. So let's consider the taffy pulling map. So once again, a taffy pulling map is you twist the first two holes by 1/2 and then the other two holes by another half. You can look at any curve C, apply those two twists, get some sort of curve, and then you do it again and again and again. And it is an observation of Thurston that you can then approximate the self-limiting object by something called a train track. So this thing is a train track. And furthermore, what's true about this train track is that when you apply your map, you get a map from the train track to itself. So what I did is that in this picture, I first did one twist and then the other, and then I ended up with this picture. And this picture is drawn in a way that indicates that when you collapse the things that lie close to each other, you get back the original train track. And so that's how you get a map from the train track to itself. And once you have such a train track, you can write down a matrix. So this matrix records how the branches cross themselves. So if you look at the red branch, in the image, it goes through like that. So it passes through the blue and yellow. So I think this row is blue, this one is yellow. And so if you now look at the blue,
But it's like an abaninization, right, of the image.
a
I mean, the image is a sequence, but then you forget about the order of the.
yes. So another example is if you look at the image of blue, it goes around like that, so it just crosses the yellow ones. So there's a 1 here. And somehow the magical fact is that if you look at the spectral radius of this matrix, it would return to you the number lambda that played a role in the definition of pseudo-Anosov math. So in this case, this would be u squared. But now the key is that train tracks are highly non-unique. So here's another train track that you could use to do the same computation. I'm not going to run through the computation, but you get this matrix. And when you look at the spectral radius of this matrix, well, you realize that this is a block matrix. And this block is 0. And this block up here is a permutation matrix. So all of its eigenvalues lie in the unit circle. And so somehow they don't really contribute to the spectral radius. So what really matters is this block down here. So I get a smaller matrix that encapsulates the dynamics of my map. And the thing that makes this work is the fact that I have these little balloons here that only go into one of the balloons. They get permuted, hence the permutation matrix. And so the key observation that Andrew and I made was that for braids in general, you can actually choose your train track to be something which we call a floral train track. Of this form. Have a center pistil, and then some filaments that connect up to anthers, which basically these little balloons here. And then you have these petals that go around the anthers and the filaments. And once you choose your train track to be of this form, you can then deduce facts about the transition matrix that you write down. And once you have enough information that gives you lower bounds to the spectral radius of that matrix, and combined with the examples of Hironaka-Kin and Fensk, you then are able to solve the minimum dilatation problem. I think I'm going to stop here because I'm out of time. I'm happy to answer any questions.
Questions?
So how unique is that braid that minimizes entropy in the sense that you?
So in the free, sorry. In the free strand setting, this is unique. I believe this is also unique. These two, I think, are unique. It's not clear whether it's unique in all other higher number of strands. I would suspect that it's not.
So here, Hironaka-Kin and Fensk braids were not minimal
They were minimal, but they might not be the unique minimizer.
because you constructed something different. No? Is that not so?
Sorry, say again?
So this two Ferris wheel you constructed, you said that was not one of their examples.
Oh,
The 1/2 case.
yeah, sorry. This is also unique. I was thinking of the Xiangzhuo case, right? Okay, so this is also unique, but then for the higher up ones, it's unclear. And most likely, I think not. It's a really bad idea to say like stuff when being recorded. Anyway, it's probably not unique.
So the line with 1/2 log in it, you said it's coming from two Ferris wheel of some other construction.
Yeah,
right?
of this thing. So this,
But you said it's not present in the examples of Hironaka-Kin and Fensk.
well, it's a Ferris wheel of their example.
But their examples for this
Like, for
order,
example, for eight, like,
n equal to 6.
Mhm.
They have a different example from a Ferris wheel?
or they don't,
So-
they don't actually have 6 if it or today. But like any 8k plus 2 is equal for
Yeah.
2k plus 2.
Okay.
So we have kind of overlap between their range and your range.
Well,
And you're
okay,
saying
so
it's
their
Ferris wheel.
examples are also Anasoff.
But are they Ferris wheel?
Their two Anasoff things are never Ferris wheels.
So, yeah, so, but you said yours are Ferris wheel, so that seems
Right,
like they
so
should be different examples.
They are different.
So there are, okay, so in that range, there are multiple, you know.
Well, no, their thing does not minimize.
Oh, it's not minimizer
Yeah.
what they did, okay.
It minimizes, it's a minimizer if you only think about two Anasoff maps.
So in the trivial examples, I mean, they're not. So you get that this spectral radius is 1, or spectral radius of the matrix that you get if you apply the train track.
So the train
On
track
the
stuff really only works when you're two Anasoff. And if you are trivial, then, well, okay, I guess I could say not trivial for the homeomorphism. But even here, this would be considered reducible. Stuff of this type, I should say, would be considered reducible.
And is there anything known about other surfaces? I mean, the entropy.
Very little, so you could ask the same question. But now allowing your surface to not just be punctured this, but maybe it's a closed surfaces.
Yeah.
Then this is known for genus 1 surface, the torus. This is known for genus 2 surface, and that's it.
So you can't have you don't have some statement that says the hyperelliptic diffeomorphisms are the minimizers, like that's wrong.
The hyperelliptic.
Somehow those are, well, they're symmetric, and then those are the one you can quotient down to braids, which you saw.
So this also gives you the minimum entropy among hyperelliptic things,
Yeah.
but the hyperelliptic things are not.
Yeah, they should.
They're not the minimum among everything.
You have examples of those?
Yeah, because we have examples of non-hyperelliptic maps that have smaller entropy, smaller dilatation than these ones. So there are definitely smaller dilatations. Yeah.
Is it anything known about the rest of the spectrum? So we know there's a gap between 0 and
So if you fix the number of strands, then it's actually a discrete. It's actually, sorry, let's see if that's right. Yeah, if you fix the number of strands, it's gonna be discrete. But as n grows, this A to n gets smaller and smaller, so it has to accumulate at 1. But I think that's the only accumulation, yeah. Yeah, it is, yeah. It must be a leak.